So let's dig in and start talking about the types of intermolecular forces. There are going to be 3 types of intermolecular forces that we talk about. The first is the most common one. The first type is called a London dispersion force, or you may see them called just dispersion forces. They are present in every liquid and solid substance. In all liquid and solid substances. The strength of them will vary depending on substances, and we'll talk about how that is. But they are also, the reason that they're present in everything is because it really just depends on the random movement of electrons in a molecule. Every molecule has electrons, and those electrons are constantly moving. And the way that these attractions occur is if at some point there is an unequal distribution of electrons. At some point, there's more electrons on one side than the other at some moment in time. Okay. So they're caused by a momentary unequal distribution of electrons. Electrons do not stand still. So at some point, it's possible that more electrons are present on one side than the other. And that's what this picture is showing. This picture shows some molecule that at this point in time has a partial negative on it. Okay, that's going to mean more electrons on this side. At some moment in time, more electrons here and fewer electrons here. Okay. And because there are more electrons on one side and electrons are negatively charged, we end up with, in a moment, in an instant, more electron density here and a partial negative that shows that. And if we have a separation of charge like this, we call it a dipole. So we say that because it's at a particular moment in time, we see more electrons on one side of the molecule, we have a temporary dipole. It's not going to stay that way forever because the electrons will continue to move, but at one moment in time, there is a dipole, a temporary dipole. And what that will do is induce a dipole in the molecule next to it. So what that means is if I've got a lot of electrons here, electrons repel each other, right? Electrons repel each other. So if there happens to be a lot of electrons here, that's going to push the electrons away on the other molecule, and it's going to make it a partial positive on this side. Okay. More electrons here will repel the electrons and force them to the other side of the molecule, making this a partial positive and this a partial negative. Okay. And then we get this weak force of attraction between a partial negative and a partial positive, right? Opposite charges attract. And so now all of a sudden, because this is partial negative and it's pushed the electrons away on the other molecule, this is partial positive, and there's a little bit of attraction there. It's a very weak attraction because it's all temporary. These dipoles are caused by random fluctuation and random motion in electrons in the molecule, and they're going to continue to move, and the dipoles will change. But we get this kind of fluctuation. So that's kind of the basics of the London dispersion force. They're temporary forces. So let's talk about the types. So London dispersion. It's going to be the weakest of the IMF, intermolecular forces. Okay. It's the weakest type. They are temporary dipoles. So they can be kind of temporary attractions. And because it's due to electron fluctuation, if we have more electrons, we have the potential for stronger attractions. Okay, so the strength depends on the number of electrons. If we have more electrons in the molecule, we have the potential for stronger London dispersion forces because you have more electrons causing the temporary dipole, the partial negative and partial positive. So we have a couple of pictures here that show the last piece of it. It'll depend on the number of electrons. So it's going to be stronger. I can even write that in here. It's going to be stronger for molecules with more electrons. And then lastly, what this picture is going to show is that it also can depend on the surface area of the molecule. How much area is there for the two molecules to interact with each other? So here we may have maybe at least 4, this might be 5 carbon molecules. All of these have 5 carbons, so all of them have a formula of C5H, what, 1, 2, 3, 4, 5, 6, H12, I think. Would each have 3 hydrogen on them? Okay, C5H12, I think. All of them have the same formula, but they're structured in a way that some are longer and some are more branched. Okay, this is something that looks kind of branched out, right? Where you might have a carbon bonded to 4 carbons, and they're all bonded to hydrogens. Okay. This one has maybe 4 carbons. This one's less branched, the isopentane. You might have a C coming off one of these. This one's a little bit less branched. Okay. But so it's got a longer, right? If we look at maybe surface area, we've got this length in the first one. We've got something a little longer in the second one. And then in the last one, it's completely linear. C, 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 1, C. And then all the H's come off of that guy here. This one is going to be even longer and have even more surface area, where 2 molecules of the longer sort can have stronger interactions. So for a greater surface area, for a more linear molecule, those forces will be stronger. So here I'll say the forces are going to be stronger for molecules with greater surface area. And so that what that means is we'll see a stronger attraction for the one that is less branched out. So this is London dispersion forces. Again, it's the weakest of the three types that we're going to look at. The next type is a little bit stronger, and it's going to look similar. The type of attraction is going to look similar to London dispersion forces, but there is a key difference. Dipole-dipole attractions are going to occur in substances that are polar, that have polar covalent bonds. So these occur in substances that have polar covalent bonds. Okay. So imagine something we already said is polar, like water, maybe, or like maybe C. Okay. If I look at this molecule, it's going to be a polar molecule. So then I would say in a sample of this substance, more than one of them, we have the potential for dipole-dipole attractions. And the name of them comes from the permanent dipole in one molecule will interact with the permanent dipole in the other. So the key difference between London dispersion and dipole-dipole is that this means that it occurs in substances that have permanent dipoles. And that's what I mean by polar covalent bonds. Occurs between molecules that have permanent dipoles, rather than the temporary dipole that we see with the London dispersion forces. So these are not present in every type of substance. Permanent dipoles. Only in polar compounds. Okay. And so the interaction comes when we have some molecule. I can even look at the HCl, would be an example that we saw earlier. Okay. HCl has a dipole, a permanent dipole, where the partial positive is on the hydrogen and the partial negative is on the chlorine. Okay. There's a permanent dipole here, and so in a sample of HCl, what we would see is an attraction from the chlorine on one molecule to the partial positive on the hydrogen on a different molecule. Hydrogen still has a partial positive. It's bonded to its own chlorine, which has a partial negative. And we have a force of attraction between them that is stronger because it's not temporary. The chlorine is permanently partial negative, and the hydrogen is permanently partial positive. So this force is going to be stronger than the London dispersion forces. So we can have an interaction like that. The intermolecular force is that blue highlighted kind of hash mark, dashed lines. The other way that we could see an interaction is shown here also, where maybe we have a hydrogen and chlorine, which is the partial positive and partial negative, and both of them are attracted to the opposite on the other molecule. So the partial negative on the second molecule is attracted to the partial positive on the first molecule. So we might see interactions, the dispersion, or the dipole-dipole, sorry, the intermolecular forces between the opposite partial charges. So you're looking at lining up the opposite partial charge. Opposite charges attract. So we can see that in these two ways. Okay, so they're stronger than dispersion forces. They're present in anything that is a polar compound. I might rephrase this. Current substances that have polar molecules. Okay. The last type of force is similar to the dipole-dipole force. It's called hydrogen bonding, and it occurs in only certain types of molecules. Hydrogen bonding is an especially strong dipole-dipole force. And it occurs in especially polar, the most polar sorts of compounds. And the compounds that can show the hydrogen bonding intermolecular force are compounds where hydrogen is bonded in the molecule to nitrogen, oxygen, or fluorine. So in the molecule itself, you need to see an HN bond, an HO bond, or an HF bond. Okay, that needs to be present in the molecule. Okay, so these guys need to be intramolecular forces that are present. So for instance, water is a good example of something that has hydrogen bonding. Water is HOH. Okay. So we're looking at the first criteria being an HO bond. We see that in water. Water has inside the molecule an H and O bond. You would also see it with something like ammonia, which is NH3. Ammonia would show hydrogen bonding because inside the molecule we see NH bonds. The hydrogen bond intermolecular force, though, is between two separate molecules that have these types of bonds. So what we're looking at is water being a polar molecule. We have a water molecule here, and we have a partial negative on the oxygen and partial positives on the hydrogen. The hydrogen bond is the intermolecular force between the partial negative and partial positive. So the interaction is similar to dipole-dipole in that we have a permanent dipole in water from the positive to the negative, right? From where the hydrogens are to where the oxygen is. There's a permanent dipole. And there is an attraction between the partial positive on one molecule and the partial negative on the other. So this one is showing us an intermolecular force between the oxygen and the hydrogen. That force is what we call the hydrogen bond. This orange highlighted portion is the hydrogen bond. It is an intermolecular force. So it is between two different molecules. The hydrogen bond is not the HN bond or the HO bond or the HF bond. That's just the qualification that the molecule needs to have. You have to have that present in the molecule in order for the intermolecular force to be called a hydrogen bond. So here, again, the hydrogen bond is the IMF between the oxygen on one and the hydrogen on the other. Okay. Let's do one more example of this before we wrap up. So we have ammonia. The other thing that I want to say or distinguish is that that maybe I have like carbon, nitrogen, H, H, H. Maybe I have a molecule that looks like this. Okay. If I'm looking at it and I ask you, what is the intermolecular force between this molecule and another of the same type? I'll even draw it out. C, H, H, H. What is the intermolecular force type? What I'm looking at first is it a polar or nonpolar molecule? We have a difference in electronegativity here, so it's going to be a polar molecule. It's not completely symmetrical. And we have hydrogen bonded to nitrogen, which fits with the rules for hydrogen bonding. We can see hydrogen bonding when hydrogen is bonded to nitrogen, oxygen, or fluorine in the molecule. So I have the potential for hydrogen bonding here where I've got two NH bonds. The N is the partial negative and the hydrogens are the partial positive. Okay. So in these cases, the hydrogen is always the partial positive and the nitrogen, oxygen, or fluorine are the partial negatives. Okay. What we're looking at is the interaction of the hydrogen part of that, right, which might be this guy, interacting with the NO or F on the other molecule. So here, the hydrogen bond will only occur between the hydrogens that are bonded on the nitrogen and the nitrogen on the other molecule. Partial negative, partial positive, partial positive. So the hydrogen bond is occurring between this hydrogen and this nitrogen. It's not going to be from a hydrogen that is not bonded to that NO or F. Okay? So these hydrogens are not going to be part of the hydrogen bond. It has to be one of the hydrogens that's attached to that NO or F atom that we've said needs to be present. The H needs to be bonded to NO or F, and then the hydrogen bond occurs between the hydrogen part of that on one molecule and then the nitrogen, oxygen, or fluorine on the other molecule. Okay. So the way the force works is similar to dipole-dipole, but there are more qualifications on it, and it can be a little bit harder to see. So first of all, you're looking for this type of bond, and then you can say it's between nitrogen, oxygen, and fluorine. You know, it's got hydrogen bonding. If I see something like this in the molecule, I can say the IMF is a hydrogen bond. And then if you were asked to draw it, you would draw it something like this, or they're showing in the text, they show how water interacts, right? The hydrogens on the O interact with the O on the other molecule. Okay, so these are the three types of intermolecular forces. And this is going to be the end of this video. Just get familiar with the types of forces and how they compare. I started off by saying that the London dispersion forces are the weakest. The hydrogen bonding forces are the strongest of the three. So in terms of strength, it goes London dispersion is the weakest, then dipole-dipole, and then hydrogen bonding is the strongest intermolecular force. Okay, So get some familiarity with that, do some practice in the homework, and I will see you guys in the next video. We're going to talk about some properties of liquids, and that one will be a short one, so I'll see you there.